Hello again, Mr. Wakefield here, and we are in the final section of what we're going to cover in Math 130, and it is a section that is completely unlike anything you've seen throughout the semester, maybe anything like you've seen in any math class even, okay? But please be patient with me. You may not understand everything at first. Okay, we're going to do plenty of problems here, and so give it a chance here to kind of give yourself a chance to absorb the information, maybe slowly but surely, but eventually you surely will, I believe, if you really try hard by the time we get to the end of this section. But it is a lot of new and interesting things that you haven't seen before. So be patient with it, okay? Let's start out with something really simple, though, to kind of help us understand what we're trying to do here, because it's so different than anything else we've ever done. I'm going to show you this problem right here. You don't have to write this down. Just look at this for a minute with me here. Okay, this problem right here, it is different than anything we've done, because what I'm going to do is I'm going to ask you to prove that this is true. Prove that this is true. Prove this, okay? Can you do that? And what do I mean by proving it? What it means when you prove something in math, and pretty much in any area of life, not just in math, is it means that if you have something that they give you here that they want you to prove, they're already telling you in advance that it's true. Okay, I'm telling you right now because I've already checked this. I already know that this statement right here is true. I know that all this stuff right here is equal to 68. Okay, so I'm not asking you to find out if it's true or not. I'm telling you that it already is. You need to now prove it. Okay, and what do I mean by proving? And why would I ask you to prove something that if I already know it's true? Because I want to make sure that you could prove it to somebody else. Do you have that ability? I could show you how to prove it. Okay. In other words, I could prove it to you. If you, like, for example, if you said to me, hey, prove this to me that this is true. Okay. I'm not convinced. I want you to convince me, and then I could go ahead and convince you. Okay. But the question is now, can you now convince somebody else? And that's what you need to learn today. Can you convince somebody else that a particular statement is true? In other words, what I want you to do in particular, because again, when you're trying to convince somebody, it's not me you're trying to convince. You want to pretend like you're convincing somebody that doesn't believe it. Okay, that's when you really know that you can prove something, is if you can convince somebody that's a skeptic, that doesn't believe it. Okay, so let's say, for example, somebody comes up to you and says, you know, I bet that this isn't true. I'm not convinced at all. Okay, prove it to me. And they ask you to prove it to them. All right, could you do that? All right, well, that's exactly what we're going to do today. We're going to be proving things. All right, and the approach we want to take is we want to imagine somebody coming up to us and saying, you know what, I don't think that this is true. Prove it to me. Show me how it's true. So let's start out with this first example, and then we'll get into the actual problems that we're going to do. Okay, the way I would prove this is to simply do order of operations right here, which is what we normally do when one side of the equal sign doesn't have any variables in it. And I will prove to you that all of this stuff really is equal to 68. Okay, so parentheses first, get 17. And then multiplication comes before addition. And so if the skeptic at this point says, hey, wait a second, you're going too fast. Why did you do parentheses first? Well, that's what you do first when you do order of operations. And then you explain that to them, that that's the rules in order of operations. Okay. And then you multiply next, and then you add. You could explain to the person that, hey, that is the order that you do order of operations in. And we need to do order of operations whenever we have no variable on that side of the equal sign, and we want to figure out what it's equal to. And so you can see here now that doing the order of operations, it truly does end up being equal to 68 here. And so the left side has now been proven to be equal to the right side. Okay, by doing order of operations, which is a completely valid thing to do and what we normally would do in this situation, we now proved that this was equal to 68 because this big thing right here on the left side of the equal sign ended up being equal to 68. Okay, so that's what it means to prove. Where you're taking something that you already know is true and you're convincing somebody that does not believe it, you're convincing them that it's true. Okay, so I just did that for you right now. Okay, now can you do that kind of thing when somebody else comes up to you and says, prove that to me, I'm not sure that it's true. Okay, I don't see it. I can't imagine that it's true. Can you then prove it to that person? All right, so what we're going to do also in addition to that is we're going to prove a multiple amount of statements here. I'll get into that here as we go along. Okay, so again, be patient here. There's a lot of stuff going on here, all right? So all this stuff here, it talks about mathematical induction. I'll explain that as we go along. It doesn't really do me any good to try to explain all this complicated looking words here right away, but this is what we're ultimately going to be doing here, okay? But let's jump right into the first problem, and then that'll be an easier way to understand what's going on, all right? It says here for each problem, and there's 4 of them, so we'll have plenty of practice. It says assume that n is a positive integer. So anytime you see n, it's a positive integer, which means a positive whole number. A positive whole number, such as what? Remember, a positive whole number is, it could be 1, 2, 3, 4, all the way up to infinity. Any one of those types of numbers. Okay? So what we're going to do is we're going to do mathematical induction, like I said, to do, and you don't need to memorize what mathematical induction is. It actually spells it out for you here step by step, so don't worry about that. Okay, but you just need to do all of these things one thing at a time. Again, I'll carefully go through each step for you. Okay, so what do you ultimately want to do? Look at this first statement here, and again, I want to explain this here. You don't have to write down what I'm about to put down on this piece of paper right here, scratch piece of paper. But what this first statement is saying, again, don't have to write it down. It's just I wrote this down so you can understand what this whole thing means. Okay, we ain't going to get very far if you don't understand what this thing means. This statement right here with the equal sign in the middle and with the fraction on the right. Okay, what this is saying is that if n is equal to 1, then this is the only thing right here on the left side of the equal sign. All this other stuff is not there. Okay, so the first statement, we're going to prove a bunch of statements here, all right? I'm going to prove a bunch of statements are true. The first statement is when you just have the first term here and then you plug in 1 here. And so you can see that here. I just got the first term, 5, and then I plug in 1 on the other side of the equal sign. All these problems are going to be like that, okay? All these problems are going to be such that when you get to the second term, or the second statement rather, S2 is the second statement, just like S1 is the first statement, okay? S means statement, all right? An equation is a statement, and these are equations because they have equal signs, so we call them statements, all right? But we need to prove that they're all true. The second statement is the first 2 terms. Just like the first statement was just the first term only, the second statement will be the first 2 terms, the third statement will be the first 3 terms, and so on. But then the other side of the equal sign, you plug in the number that is underneath the S right here, okay? See how I plugged in 2 into the N right here? Okay, 2 and 2 plus 1, n and n plus 1, so I plugged in the 2. If you have S3, then you plug in 3, so we got 3 and 3 plus 1 in the place of n and n plus 1 right there. Okay, and then if you get to the fourth statement, it's the first 4 terms. And as you can imagine here, even though it doesn't say it here, the next term here is 20, isn't it? Okay, if you follow the pattern, it's like a sequential pattern. We talked about sequences earlier in this chapter, didn't we? Okay, can you prove all these statements along with all the other ones that happen after that? Okay, well, fortunately, we're not going to have to do it one statement at a time because you would never be able to do that since these statements go on forever and ever and ever. You would never get to the end of it. There is a better way to do it, though. Okay, we'll get into that. Again, be patient here. All right, a lot of stuff going on. The first part here is the easiest part, though. All right. It says to verify. Now, let me get this out of the way right now. Verify is just another word for prove. Okay. If it says to verify something, it means to prove it. Okay. So it's saying prove that this statement, when n is equal to 1 right here, prove that that thing's true. Let's write it down first, and then we'll prove it. Okay. Or verify it, same thing, okay? And both of those words are truly saying the same thing, have the same meaning. So I wrote it down. That's the first statement, okay? They want you to prove that that's true. Just like this problem we did earlier here, where I said prove this, right? If one side has just a single number, then what we usually do is we take the more complicated side and we try to simplify that. All right, and when we simplify something that doesn't have any variables in it, again, we use order of operations. Okay, so I'll take the more complicated side right here, the fraction side, and I'll do order of operations on that, and I will prove that it's equal to 5. Now remember, we already know that this thing is true. They would not tell us to prove something unless they've already verified in their own mind that it's true, and now they're asking you to prove it. Okay, so we know that this is true, all right? If you end up getting two numbers that are not equal to each other, you definitely did something wrong because it's definitely supposed to be equal. That's why that equal sign is there, okay? So this fraction, when you put it in, when you do order of operations on this fraction, it had better be equal to 5 or something went wrong, okay? So let's keep that in mind. But remember, when you do order of operations on a fraction, if you just have a fraction and no other stuff outside of it, that means that you figure out what the top and bottom are equal to first. We've done that a number of times throughout the semester when we have just a fraction, one big fraction. So the top, we got to do order of operations on that. The bottom we already know is equal to 2. So parentheses first on the top, and then multiplication. 5 times 1 is 5. 5 times 2 is 10. And as you can see here, and again, just a reminder, when you are doing order of operations on a fraction, after you figure out what the top and bottom are equal to, and we got 10 and 2 now, then you put it in lowest terms. But as you know, when you put 10 over 2 into lowest terms, that would be 5 over 1, wouldn't it? Which is, what is 5 divided by 1? It is equal to 5. So we did it, you guys. We proved that the more complicated side was equal to the simpler side. But the important thing is that we proved that the two sides were equal. Okay? When they say to prove something and they have an equal sign in the middle of it, they're trying to get you to prove that the two sides truly are equal. We just did that right here at the bottom. We did it. Okay? So as soon as you've done that, you can move on to the next part of the problem, part B. This is where it gets a little bit more complicated. So again, that's why I keep on saying to be patient. Okay, so just bear with me here. It's going to be a little bit weird at first, but I'll explain it as carefully as possible. It says write the statement for NK. All right. Let me show you what I mean by that. We know that S1 looks like this. So we know that S2 looks like this, and 3 and 4. So what about for K? You might be wondering, well, wait a second. I don't know what number K is, all right? I don't know if it's 1, 2, 3, 4, or something else. Okay, but look at the formula. Okay, for the formula, it keeps on going until you get wherever it ends, they put the n right there. Okay, so in other words, what that means is that since n is equal to 1 in the first, remember the little number underneath the s is the n. That is the n number. Let me write that down up here at the top. Sn. So whatever that number is, that's the n number. That's why I always plugged in the same number on the other side of the equal sign. For S1, I plugged in 1. For S2, I plugged in 2, and so on. Okay. So notice though that these if you look at the left-hand side of the equal sign, what's the last number in each case on the left side of the equal sign? The last number is 5, and this one is 10, and this one is 15, and in this one is 20. Okay, so notice that it's not a coincidence that the last term is 5 times 1, 5 times 2 when it's S2, 5 times 3 when it's S3, 5 times 4 when it's S4. Okay, that's why it says right here 5 times n. It means that whatever the n number is that's next to the s, if you multiply that by 5, that will be the last term on that side of the equal sign. So that's why they got that 5n right there. I just want to make sure you understand that, because that's going to help us on this next part here. So if k is the same thing as n, which is what they're saying here, okay, they're saying that they want you to do n equal to k. All that they want you to do here, you guys, is just to take the same statement and replace the n with k. That's all that they want you to do. I know that seems so almost too simple, and we're just replacing one letter with another. Okay, but there's a reason behind that, as we'll see here. Let me write this down. So all I'm doing is I'm replacing the n with a k. All right. So that's B. Part C, they tell you to do exactly the same thing. Only instead of replacing the last part there with k, you're going to replace it with k plus 1. Okay. Now, you need to understand something here, though. Okay. When you plug, when you do sk plus 1, that's always the next statement. K plus 1 is always the next statement after sk. There's no statements in between sk and sk plus 1. Okay, so when I write this out, because of the fact that those two statements are next to each other, all right, and you don't need to write down more than 5, 10, 15. You don't need to say 20 like I did here. Okay, that was just for a specific example. I'm just following the same formula here. Just copy it right off of that, bring it down. But one additional thing I want you to do, since the k plus 1 is the next statement after sk, and since each statement always has one, notice how each statement has one more term on the left than the previous statement. One term, 2 terms on the left, 3 terms on the left, 4 terms on the left. Each statement always has one more term than the previous one. So since sk plus 1 is the next term, okay, or pardon me, is the next statement after sk, which we just wrote down, wouldn't it make sense? And even before I say that, I'm going to leave an open space right here. Don't write anything there. I'll fill that in a minute. But the last statement, or the last term in the sk plus 1 is supposed to be this right here. I'll explain it, don't worry. Okay, but it's supposed to be that right there. Okay, because remember, if the last term is supposed to be 5n, and if the n is supposed to be equal to k plus 1, that means that the last term on that side of the equal sign should be this same term with the k plus 1 plugged into it. So 5 and then k plus 1 gets plugged in. And use a bracket right there because it's got 2 terms. All right. Normally we put a bracket around k because we plug that into something. But since it doesn't matter if there's a bracket, it's still going to be 5k with or without the bracket there. But when you plug in 2 terms, you definitely need to use the bracket there. And k plus 1 is 2 terms. Okay, so just like all the rest of these, you guys, all right, S1, the last term is 5 times 1. S2, the last term is 5 times 2. S3, the last term is 5 times 3. It makes sense that for sk plus 1, the last term would be 5k plus 1. Okay, but what is this missing term then? Well, you'll notice that the last term in the previous statement is always the second last term in the next one. Okay, 10 is the last term here. Now it's the second to last. 15 is the last term on this one. Now it's the second to last one. Whatever was the previous final term will now be the second to last term in the next statement. And so if sk plus 1 is immediately after sk, then that must mean that the last term right here in the previous statement then becomes the second to last term in the current statement. So I just want to make sure you understand, because this is going to be really important for the part D, which is the toughest part of all, okay? But we're making it easier. I wanted to make sure you understood that the last term in part B here on the left side of the equal sign will always be the second to last term before that final plus sign that is outside of a bracket. This plus doesn't count. The last plus that's outside of a bracket there, what goes before that? It's the last term in the previous statement on that side of the equal sign. Okay. Again, a lot of stuff that I'm throwing at you here. Don't worry. Okay. We're going to see lots of examples. It's going to get easier as you see this process played out over and over again repeatedly. Okay. What's on the other side of the equal sign? Well, since this is the k plus 1 term, k plus 1 statement, you're supposed to plug in k plus 1 wherever the n is. All right, just like S1, you plug in 1, S2, you plug in 2, S3, you plug in 3, and so on. For SK plus 1, okay, SK plus 1, that statement, all right, that's what I'm writing down right here. That is going to be this right here, 5, and then you plug in k plus 1 into the place of n. So the n right here gets replaced by k plus 1. So then I plug in k plus 1 here. And what is k plus 1 plus 1? Okay, remember that plus 1 was already there. So if I plug in k plus 1 next to it, that's going to be k plus 2, isn't it? Okay, all over 2 still. All right, so I'm actually going to write down something here. Hold on just a minute. I'm not changing anything. I'm just going to be a little bit more thorough here in what I wrote down. This right here, as we just found out, is the SK statement. That is the SK statement right there. Let me zoom in a little bit for you. That's the SK statement right there. This one right here is the SK plus 1 statement. All right, which is always the next statement after the SK statement. SK plus 1. All right. Okay. Okay, now here's where it gets interesting. Not that it wasn't interesting before. Okay, I know it's there's a lot of new stuff here. So that's part B and that's part C. Part D is, let's read it. It says, assume that the statement is true for NK. In other words, it's saying, assume what? Assume that SK is true. Okay, they want you to assume that. That means it's okay to pretend, or you're not pretending, it's for real, but it's okay to imagine that that's true. Okay, and then use algebra to change the statement. I'll show you how to do that in the part B, which is that same statement, to make it look like the statement in part C. Okay, and I'll explain what that all means, all right, why we're doing that. But for now, that's we're going to take this statement right here, part B. Let's go ahead and bring that down. So bring that down here, the part B statement. Let me give a little bit more room here. Hold on. So I'm going to bring that down. Just the part B statement, you guys, not part C yet. We'll get to that in a minute. Here's the part B statement. Okay. And actually, pardon me, I meant to put something in between here. Excuse me. I'm sorry, I keep on erasing things. Leave an empty space right here, about that big. You'll see why I'm putting it there in a minute. Leave an empty space right there. And then put that fraction that I just wrote down and erased, put that on the other side. Okay. This is still the same statement as part B. I just left an empty space right there, but the empty space is nothing yet. So it's still the same statement as part B. So I brought that down, and they want you to imagine that that's true. Assume that that's true. Okay. You might be wondering, I don't know if that's true or not. Well, I'm telling you that that's true. I guarantee you that that's true. Okay. You can assume that that's true. That's okay with me. All right. That's okay with the people that wrote this problem. No doubt about it. All right. So even if you're not convinced, all right, that is true. All right. So here's what we're going to do. I want you to take the last term on the left side of the equal sign. We're going to do this each time. It's nice and consistent. I want you to take this last term, the last part here after that last plus sign that's outside of the bracket, not including this plus sign. This last plus sign, I want you to take that last part right there, 5k plus 1, and I want you to not only add it to, sorry, my pen needs there it goes. Okay, it's working now. Again, you don't need color here, but I'm just doing the color here for emphasis. I want you to add 5k plus 1 to both sides of the equal sign. Okay, both sides. Why would I do that? Okay, let's back up for just a moment. The original thing I wrote down here in part D, not including the red part, the original part I wrote down in pencil, okay, we were allowed to assume that that was true. That was the part B statement. Okay, they told us we can assume that that's true. Let me show you something here for a moment. 3 equal to 3. 3, actually, yeah, I'll go and write that down. 3 equal to 3 right there. We know that that's true, right? We can assume that that's true because we know it's true, right? Okay, well, what if I did this? What if I took those two numbers that I already know are true, that are definitely equal to each other, and I added the same amount to both sides? Is it still true? Is the resulting statement here true? Yeah, it's 7 equal to 7, right? In other words, and this is why we do this a lot when we solve equations, if you have something that is definitely true, 3 equal to 3, and you add the same amount to both sides, it's still true. And that's why you do that when you solve equations a lot of the time. It's because when you add the same amount to both sides, it's going to take something that's true and it keeps it true. So it doesn't ruin the problem or anything like that. Okay, it's still true. And so we can do that here. And that's why I did this here in part D. I took something that we already assumed in pencil was true because it came from part B, and then I added the same amount to both sides. Okay, now let's back up for just a moment. You might be wondering, well, wait a second. How am I supposed to know when I do my homework or do an exam question, how am I supposed to know to add that to both sides? Well, you always, as I believe I mentioned a few minutes ago, but I'll go and mention again anyway, you always add this last part here, the part that's before that last, right after that last plus sign that's outside the bracket there. You always add that to both sides in part D. Every single time, I promise you, okay, that's exactly what you want to do. All right, you can count on that. All right? So then what do we do next? What I want to now do is, here's the thing now. Since I added the same amount to both sides, then just like the 7 equal to 7 example here, okay, we can now assume that this resulting statement that I got right here is also true. So the part B statement, we were allowed to assume that that was true. And since I added the same amount to both sides of that part B statement, the resulting statement I have here, including the red stuff, okay, that I added to both sides, that's true also. We can assume that too. All right. So what I'm going to do now is I'm now going to prove to you that this right-hand side of the equal sign, and I'll tell you why I'm doing this after I'm done, okay? But I'm going to prove to you that the right-hand side of this equal sign is equal to this fraction up here on the right-hand side of part C. You're always going to do that. You're always going to take the right-hand side of part D, and you're going to prove that it's equal to the right-hand side of part C. Let me say that one more time. You're going to take the right-hand side of part D, and you're going to prove that it's equal to the right-hand side of part C. Okay? Every single time. So, again, you're going to get used to this the more you do it. Okay? Don't worry. How do we do that? Well, notice that part C on the right-hand side is a single fraction. Okay? This is not a single fraction. In fact, it's a fraction plus something else. Whenever we have a fraction plus something else that's outside the fraction over here, and we want to make it equal to a single fraction, what we do is we turn this one into a fraction, and then you get a common denominator since we're adding the two new fractions together here. Okay? And then we try to make it equal to this. How do we get a common denominator? Well, if you've got denominators that are equal to 2 and 1, anytime you have one denominator equal to 1, then the other denominator, if there's only one other one, is always going to be your LCD. So because the LCD is 2, we multiply the top and the bottom of this one by 2 in order to get it to equal the same denominator as this one. Let's see what we get. We get 5k, k plus 1 over 2. Remember, that fraction stays the same because it already has the LCD sitting on the bottom right there. Okay. And then on this one right here, you multiply by, how do you multiply? How do you multiply when you have a term that's outside the bracket times a bracket times another term that's outside the bracket? So you got two terms that are outside the bracket, one bracket. All three of those things are being multiplied together. How do you do that? The way you do that usually is you multiply the two terms that are outside the bracket, and then you can then multiply the 10 times the bracket after that. But I'm going to do something different here, and you'll see why here as we go through a few more problems. But actually, you know what? I'm going to go ahead and do. I'm going to go and do it the way I originally was going to here. I was going to do something different, but there's an easier way. What's important is that we're able to understand this as well as possible. What do we normally do when we get a common denominator and we're getting ready to add? We what? We distribute out our parentheses. We saw that back when we reviewed adding and subtracting fractions in the prerequisite review packet. Okay, so 5k squared plus 5k on that one, 10k plus 10 on the other one. All right, and then we add those together. So yeah, as we did back, here's the prerequisite review packet. When you before you actually add the numerators together and keep the denominator the same, that's what you do when you add fractions, assuming the denominator is the same. Okay, and it is in the current problem, it's 2 and 2. You have to get rid of those parentheses there, the x minus 1 and the x plus 4. Then you combine the like terms in the numerators. What happens if I combine the like terms here after I distribute out those brackets? Let's find out. I get 5k squared plus 15k. Sorry, that came off the screen a little bit there. There it is. 5k squared plus 15k plus 10 all over 2. Okay. Now, if I factor this thing, okay, because here's the thing. Your goal is to make it look like this. We already have the 2 on the bottom, so we're good with that, all right? We want to make it look like this thing right here, the right-hand side of part C. Since the 2's already there, don't mess with that. We got what we want on the bottom, but how do I make the top look like this right here? It currently looks like this. Well, it looks like they factored this thing, right? Okay, well, notice there's a GCF here, and no surprise, it's 5, okay, because there's a 5 right there, so it's not a surprise that that happened, okay? And then what happens if I factor the leftover bracket here? Okay, if I factor that thing using the Berry method, which we learned to do in the prerequisite review packet when you have k squared, k to the first, and then no k at all, we end up getting... let's go ahead and take a look at that. A little review here. Let me pull that out. Give me just a moment here to find that. Here it is. Bring that out here. So when we had that type of situation, you figured out what the numbers were, okay, that would fit according to the first and last number, and also according to the middle number. I'll let you review that if you need to review that. But we go 1 times 2 right here. 1k squared and 2. 1 times 2 is 2. But it needs to add up to the middle number 3. So what two numbers add up to 3 but also equal 2 when you multiply them? The answers are 2 and 1. So that means that this is going to be k plus 2 and k plus 1. Okay, and you don't need to do the last step of the Berry method there where you factor out the GCFs because the GCFs are already equal to 1, so nothing's going to happen if you try to factor those out. But look at what I just did, you guys. I did it. I did exactly what we needed to do. I said that I needed to take the right-hand side of part C, and I needed to prove that it was equal to this. I just did it. Throughout all these steps that I just did, I proved that the right-hand side of the part D statement, which is this thing right here with the red thing, throughout all these steps, I ultimately proved that it's equal to the right-hand side of the part C statement. Okay, so you might be wondering, well, great, what does that all mean? Okay, what is the point of all this? Okay, great question. It's an understandable thing to ask that. Okay, but what we just proved is... that's right there, and this is part E. We just proved that whenever, and I'll explain why in a second here, hold on. Whenever SK is true, SK plus 1 automatically is true as well. In fact, I'll write down the word also just for extra emphasis. Okay? I'll explain here, hold on. Whenever SK is true, SK plus 1 is also true. Why can I make that claim? Okay, here's what I did. I took SK, that statement, part B. I wrote it down, and I said, this is true. We're going to assume that that's true. And based on the fact that that was true, I then took these two red things and I added them to both sides. And since they were both the same thing, SK plus 1, as we said, if you take something that's already true, which is in pencil here, the part B statement, and you add the same amount to both sides, you can now say that that resulting statement is true. But that resulting statement with the red stuff in it, all right, that statement, which we just found out is true, it is the same thing as part C right here. On the left-hand side. See how the left-hand side of the equal sign is the same for both part C and part D? Exactly the same. Okay, so if I can then prove that the other side of the equal sign, the right-hand side, if I could prove that those two sides are equal, and I did, okay, I proved that the right-hand side of part D was really equal to the right-hand side of part C, okay, that then proves that the part C statement is true. Okay, so whenever the part B statement is true, we prove that automatically that leads to the conclusion that the part C statement, which is the SK plus 1 statement right here from part C, we can now claim that that's also true as well. What does all this mean, though? Let's talk about that. Well, we already found out earlier in the problem over here, the very first part here, we found out that the S1 statement was true. Okay, so let's write that down. Since, and say that word since, that's important. Since S1 is true, okay, this statement right here is telling me that whatever statement you have, the next statement's automatically true. You proved that in part D. That's why it's so important, okay? We just found out that no matter what statement you're on, the next statement's automatically true. So since we proved that the first one is true, that automatically means that the next one is true, right? So we've now proven that the first two statements are true. Why? Because I proved that the first one was true all the way back at the beginning of the problem. But then this thing right here, this sentence right here, that I just wrote down, SK and SK plus 1, that means that whenever you have a statement that's true, that you've already proven is true, you can then say that the next one's true automatically. You're allowed to do that after you prove part D. You can do that. You got to do part D first. But we did it. So now that I've proven that S2 is true, along with S1, which I proved way over here, I can now say this. Since S2 is true now, what does that mean? Well, this statement up here says that if S2 is true, then the next one is automatically true as well. S3 is now true. So now I've proven that the first three are true. But again, the thing that I proved here in part D means that if S3 is true, which I just proved on the last sentence, since S3 is true, what's the next statement? S4. And that's true now too, because when one statement is true, you guys, the next one is true automatically. Whenever you get done with part D, you guys, you have proven, assuming you did part D correctly, you have proven that each statement in the problem, if it's true, then the next one is true automatically. So can you see that this is just going to go on forever? S4 is going to lead to S5, S5 is going to lead to S6, and this is going to go on forever and ever and ever. Okay? And so that's what we ultimately need to do, is to prove that it's true for every single statement, okay? Not just for the first 4 statements that I wrote down earlier, but for all of them going on forever and ever and ever. Okay, but we've already pretty much proven that it's true for any statement, even the ones that go on forever and ever and ever, because you can see that this sequence is going to continue to S5 and S6 and S7 and S8 and so on forever and ever and ever, okay? So what I'm going to do is I'm going to write down the 3 words "and so on." That means that it just keeps on going in that same pattern. Okay? So here's the final statement, and then the problem will be done. Thus, Sn, which is the general statement at the beginning of the problem, this thing right here, the original problem, that is the Sn statement. Okay? That thing is true for any n that you plug into it. Any n, whether it's 1, 2, 3, 4, all the way up to a million, a billion, any number. Okay, Sn is true for all n that you could possibly plug into it. Okay, and the problem's done. Lots of stuff, as I said, going on there. Again, if you're still trying to get a grasp on a lot of things that just happened, I totally understand that. Okay, not expecting you to understand everything on the first problem. Okay, let's do another problem here. And the good news is that the process of the problem is going to be virtually identical. The only difference is that when you do on part D right here, where you try to make the right-hand side of part D equal to the right-hand side of part C, that part's going to be different. Other than that, you guys, the process is going to be the same on all 4 of these problems, exactly the same. So it's going to get easier and easier as we keep on doing the same process over and over again. You'll get used to it. Okay, so let's try problem number 2. Okay, so again, they want us to verify it for n equal to 1. That means to plug in n equal to 1 on the right-hand side, but also remember, the first statement is always just the first term. So it's just 1 to the third. S2 would be 1 to the third plus 2 to the third. S3 would be 1 to the third plus 2 to the third plus 3 to the third, and so on, like that. So S1 would just be 1 to the third on the left-hand side of the equal sign. On the right-hand side, you plug in n equal to 1, just like I did in the last problem. You can see I did that up here. Okay, so what do I get? I get 1 squared, 1 plus 1 squared over 4. Let's prove or verify that this is true. Okay? How do you do that? You figure out what each side is equal to. On the last problem, I just had to figure out what the right-hand side was equal to because we already knew that the other side was equal to 5. There was nothing to figure out there. Here we have operations on both sides that we need to compute, and so we just need to figure out both sides then. Okay? Keep the sides separate, though. But figure out what they're equal to. Okay? Keeping them separate and doing order of operations on both sides, and then you'll end up finding out that they're the same if you do it right. Because like I said, when they ask you to verify something, it means that they're already telling you that this is true. This is definitely true. You just got to prove it to somebody who is not convinced. What is 1 to the third, you guys? It's equal to 1. Is this equal to 1? Yes, it is, but we got to prove that, okay? Pretending like we're talking to somebody that's not convinced. So you can't just say, oh, hey, it's obvious that this is equal to 1. No, you can't do that. That's not proving it. Okay, proving it means that you're proving it to somebody, again, like I said earlier, that is not convinced. Okay, so you can't say it's obvious. You can't say, oh, well, Mr. Wakefield's reading this and he already understands it, so it's obvious to him. No, 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 you can't do that. You've got to, again, prove it to somebody that's not convinced. So no obvious statements. Okay, you can't just say, hey, it's obvious. It'd be nice if you could say that, but you can't say that. So since this is a fraction here, figure out what the top and bottom are equal to first. Parentheses first. Okay, then exponents. I get 1 times 4. Then multiplication, and we end up with 4 over 4 equal to 1. Is that true? Okay, well, if I put this in lowest terms right here, 4 over 4, and that's what we always do with a fraction that doesn't have variables in it after you figure out what the top and bottom are equal to. Okay, you put that in lowest terms, and yes, it's equal to 1. 4 divided by 4 is 1. So we proved it. Okay, not by saying that it's obvious, but by actually going through it step by step so that somebody who's not convinced will now be convinced. Anytime you're trying to prove something to a skeptic, you got to go through it step by step very carefully. Otherwise, they're going to think that you're wrong because they're already thinking that you're wrong. So you got to bring them from thinking you're wrong to thinking that you're right. And so you got to be very detailed. Otherwise, you ain't going to convince them. Okay? What's the next part of the problem? What you do is you write down the SK statement, just like we did in the last problem. That means to simply plug in the K in wherever you see the N. Let me do that. So again, it's exactly the same thing as the statement that you see at the top of the problem here. You're just simply replacing the N with a K. It's not meant to be anything more than that. Okay? So the other side of the equal sign is going to be K to the third. K plus 1 to the third. I'm sorry. Oh, my bad. K squared, excuse me. There's squares right here, not cubes. K squared, K plus 1 squared over 4. Okay? And then what? Then we need to write down the SK plus 1 statement. Okay, again, just like in the last problem, the way you do it is you write down the same exact thing that you have in the part B statement, the same exact thing on the left. Okay. I see what, okay, I've got to be careful here. On the left-hand side, there's cubes. On the left-hand side, there's cubes there. I apologize. I wrote down 2 to the second here, and I did it again here. I need to be careful. So it's 1 to the third, 2 to the third, 3 to the third, all the way up to K to the third, but over here it's squares. Okay. So I need to be careful, and you be careful as well, okay? So you write down the same thing we had on the left-hand side. Okay, you see how I did that up here? Same thing. I wrote down the same thing on the left-hand side all the way down to the 5K, all right? And then the 5K plus 1 went after that. How did I find the 5K plus 1? You took the K plus 1 and you plugged it into here. So I'm going to do exactly the same thing. I'm going to take the part that is in the previous statement, part B, on the left-hand side of the equal sign. I'm just going to bring that whole thing down. I did that. And then I'm going to take the K plus 1 and I'm going to plug it into this N right here. And that makes that what? That makes that K plus 1 to the third. Don't forget that plus in front of it. You're always going to have a plus in front of that. Okay? And then what's on the other side of the equal sign? Not the same thing. On that side, it's the same thing as what we've been doing, though. You replace the N with K plus 1. So that's going to be K squared. I'm sorry, K plus 1 squared, excuse me. K plus 1 squared. And because the N got replaced by K plus 1 right here, so K plus 1 squared. And then this N also gets replaced by K plus 1. Just like it did up here, we replaced the N with K plus 1 in the part C statement here on the right. Okay, so K plus 1 squared, K plus 2 squared. Where did the K plus 2 come from? I plugged in K plus 1 right here, so we get K plus 1 plus 1. K plus 1 plus 1 is K plus 2. All right? Divided by 4. Again, that's from here. The 4 on the bottom is from here. Okay, now, what did I do in part D before? What I did was I took the part B statement, bring it down, just the part B statement, bring that down, but leave some space at the just before the equal sign, okay, and also at the end. Okay, again, I'll show you how to do that. I did the same thing on the last problem. Okay, so there's the left-hand side of the part B statement. Leave some space right here, okay, and then write down the other side of the part, not the part C statement like I almost did, the part B statement. Okay, there it is right there. And so that we're allowed to assume that that's true because that's the part B statement. Part B statement that says assume that that's true. It's okay to do that, and then prove that the part C statement is true. And the way you do that every single time, without exception, and we did this in the last problem, is you take this thing that is the final part of the previous statement here, the part C statement, and you add it to the left-hand side so that the left-hand side of the equal sign now, including the red part that I just added, is now exactly the same as, not the part B statement anymore, but is now exactly the same as the part C statement because you put the k plus 1 to the third there. Okay, so you add that last part so that it's the same as the part C now instead of the part B. But on the other side, okay, you add that same thing. You don't make it look like this right away. You're not allowed to do that. You have to add that same amount that you added on the left. You got to add that to the right. Okay, so just like I did in the last problem, you add the last part of the part C thing on the left, you add that to this side, but then you add that same thing to the right side also. Okay, so now what you do is you, just like we did in the last problem, you take the right-hand side of the part D statement right here that I'm looking at right here. I'm circling it with my pencil. And I then prove, by using algebra, like I did in the last problem, you prove that this thing right here is equal to the part C thing on the right-hand side. So you prove that this is equal to this fraction right here. Okay? Is this thing that I circled down here equal to this thing? Yes, it is. I guarantee you it is. Otherwise, they would not ask you to prove it. But we got to verify that for somebody that's not convinced. Okay? How do we do that? We're going to do the same thing we did in the last problem because, again, just like the last problem, we have a fraction being added to something that's not a fraction, but we need to verify that it's equal to just this one single fraction up here. Just like we did up here, we had a fraction being added to something that originally wasn't a fraction before I put the 1 underneath it, and we want to verify that it's equal to this single fraction up here in the part C statement. Okay? So what I do is the same thing. I put it over 1. I then get a common denominator, and anytime you have two denominators and one of them is equal to 1, automatically the other one is your LCD. And so I'm going to multiply the second fraction by 4, just like I multiplied the second fraction by 2 up here, in order to make the denominators the same. The first fraction stays the same because the denominator already is what you want it to be. Okay. Now, how do you multiply 4 times k plus 1 to the third? Well, first of all, you don't distribute the 4. You don't distribute a 4 to a bracket if the bracket's being taken to a power. You're not allowed to do that. Okay, if it had just been k plus 1 without the exponent, then you would distribute the 4. But not when it's taken to a power. So what I'm going to do, at least for the moment, is I'm just going to write down 4 in front of the k plus 1 to the third because it's being multiplied by it. And we usually put... when you have a single term times a bracket, you usually put the single term in front. Okay, so here's the thing. In the last problem, when I got the common denominator, I distributed out the brackets so that I can then combine like terms. Can't distribute this time because of those exponents that are attached to the brackets. Okay, so here's the thing. If you don't have any exponents attached to the brackets right there, and you want to figure out how to add those numerators together because the denominators are the same, okay, if there's no exponents attached to the brackets, then you can distribute out the brackets and then combine like terms. But if the exponents are attached to the parentheses, then we're going to do something a little bit different. Okay, listen closely here. I'm just going to write it down off to the side here. I want you to pretend, notice that those two brackets are the same, k plus 1 and k plus 1. I want you to pretend like those two brackets, and you can only do this if they're the same. I want you to pretend like those are just variables. Like I'll just call it z. Okay, so in other words, let's say you had k squared z squared. So I'm pretending like that bracket is a z. I'm just showing you how to do this when the exponents are attached to the brackets. It's something we haven't seen before, and so it's going to help us understand what to do. Okay. So there we go right there. So what do we do here? Well, what we normally would do here is since the denominators are the same, we add the numerators together. But since these are not like terms, we just simply say that they're being added together, but you don't combine them. You don't combine them, right? Okay. But can't I factor the z squared out of this? Isn't the z squared an LCD right there? Or not an LCD, a GCF? Okay. Again, you're going to see how this all ties in. Don't worry. There's a purpose to this. The z squared is the GCF here, so I could factor that out. What do I got left? I got left k squared plus 4z, don't I? If I factor out the z squared. Just factor out the GCF. Okay? And so, why did I do that? Well, what is z squared, you guys? Z squared is the same thing as k plus 1 squared because k plus 1 and z are the same thing. Okay? K plus 1 is the same thing as z. All right? I wanted to make it into z so that it would be easier to factor it, okay, without having to distribute it out because we can't distribute it out. And so, again, when you have a bracket taken to a power and both of the brackets are the same here, I would do this strategy here, pretend like it's a variable, and then after you factor it out, then put the bracket back in. What would it look like if I replaced the z back with the bracket again? It would look like k plus 1 squared. I just replaced the z with k plus 1, and then you get k squared plus 4, and then replace the z with 4k plus 1 there as well. Like that. Okay. Remember, our goal is to make it look like this right here. The statement, the right-hand side of part C. Doesn't this look almost like that? We're almost there, you guys. Okay. The k plus 1 squared is there, and it's here. The 4 is on the bottom, and the 4 is on the bottom. So if I could just prove that this bigger bracket right here is equal to k plus 2 squared, then I've proven it. Let me go ahead and write this down here, though. So this ends up being equal to k plus 1 squared. I'm just taking it off of here. Okay, I proved by making the k plus 1 into a variable, factoring out that variable, and then putting the bracket back in there. I proved that these two fractions right here are equal to this. And I'm just rewriting what I have right here. I proved that they are equal to this right here. I'm just rewriting what I already have on this scratch sheet of paper over here. Okay? But what is this thing equal to here? Can I prove that it's equal to k plus 2 squared? Well, when you have a bracket inside of another bracket, what you oftentimes do, and this is no exception, is you distribute out that inside bracket, not the outside bracket, but the inside bracket, and we get k squared plus 4k plus 4. You see that there? K squared plus 4k plus 4, I just distribute the 4 right here. And again, the k plus 1 doesn't have an exponent on the outside of it, so it's okay to distribute the 4 there. But isn't it true that if I factor that that bracket right there by doing the Berry method, okay, just like we did on the last problem when we had to do k squared plus 3k plus 2, all right, k squared plus 4k plus 4, guess what that's equal to? It is equal to let me go ahead and write it down here and catch up. It is equal to k plus 2, k plus 2. This thing right here, you guys, this thing right here is equal to these two brackets. Okay? But what is k plus 2, k plus 2? It is the same thing as k plus 2 squared. And so we did it. We proved, again, just like in the last problem, we proved that the right-hand side of the part D statement is equal to the right-hand side of the part C statement. Okay, which then means what? That means what as we get into part E? That means that, and you can say it exactly the same way in all four problems. You can memorize that. In fact, please memorize that. Okay, because as long as you say it exactly the same way I say it, you're good. Okay? It's not something where you need to put it in your own words, and I've got strict rules about making sure that you did it right. I mean, I do have strict rules about that because I got to make sure you understand how to explain it to somebody. But yeah, you can say it the exact same way each time here, and also on the test and the homework you can do that as well. How do we say this? See all these sentences I have here in part E? Your part E, you guys, assuming you do the first four parts, A through D, correctly, you can say part E exactly the same each time. It's just like rewriting the same words over and over again for each problem. Okay? And if you do that, you'll be fine. Okay, so whenever SK is true, SK plus 1 is also true. What does that mean? That means that since S1 is true, because of what we proved in part D, that whenever one statement is true, the next one that goes right after that is automatically true. So since S1 is already true, because we proved that at the beginning of the problem, okay, then S2 is true. Do you see, though, that how important it is that we have to prove S1, though, first? Because if we don't prove S1, we can't say that S2 is true unless we've already proven that S1 is true. Okay, you got to have a starting point. S1 is our starting point because it's the first statement. But since we have that starting point, S1 then being true automatically means that S2 is true. And now that S2 is true, since that's true, we can then say what? We can then automatically say that the next statement, S3, is true. And you keep on doing this. Since S3 is true, then what? S4 is true automatically. And so on. See, I'm just rewriting the same exact sentences in part E that I did in the last problem. Okay, so what's the last sentence that I said in the previous problem? And I'll just rewrite it here. Thus, Sn is true for all n. And there you go. All right. Excuse me. There we go. And so that's that's number 2. Couple more to go here. Again, it should get a little bit easier each time. And like I said, these last 2 problems, you guys, the process is going to be exactly the same, other than this part here where you try to prove that the right-hand side of part D is equal to the right-hand side of part C. That's the only part that's going to be different, okay, in each one of these 4 problems. The entire rest of the problems are exactly the same as far as the steps that you do, the process that you go through, okay? Okay, we're going to stop the video right here, and we'll have a second video that'll be a little bit shorter, just containing these last 2 problems we still need to do. So let's go ahead and stop right here, and then join me back for part 2 of section 7.5.